Welcome back, and here we go. I grabbed these entries from the table in fall 2019 test 3. So a primary allylic C bonded to H is negative 289. Why is it negative? Good question. Why is it negative? Well, we made it. It's a new bond. Secondary allylic C bonded to Cl is negative 284. Which one is faster? You want me to give you the whole answer? Here's the whole answer. In reactions where delta S, that's the change in entropy, in reactions where delta S is close to 0, delta H can be used to predict the spontaneity of a reaction. A reaction is more spontaneous with a more negative delta H. So it'll be a more negative delta G, because when delta S is 0, delta H is almost the same as delta G. And these are numbers without units. So I always cringe a little bit. Yeah. And which one happens faster? The more negative it is, the faster it happens. So over a given interval of time, this molecule will occur faster than this. So there'll be more of it than the other. So there you go. When resonance is involved, you have to look at both resonance form outcomes and pick the one that has the more negative delta H for the making of the new bond. End of that story. Now down here, we have one more example. We have two benzylic positions. Every other position is meaningless because benzylic and allylic dominate when they are options. And I think, I hope you like the secondary benzylic because it's faster to break this bond than this bond. I'll prove it to you. We got the C, well, we already proved it. Don't we have everything on this page? 360 for the primary allylic. No, we have it all over here. I don't need to get it. Primary benzylic 368. That's going to be slower to break this bond than this one, which is secondary 365. Same kind of argument as our previous discussion. Which one happens faster? In general, it's the one that's more negative. Okay, these are both positive, both kilojoules per mole, but you know, which one's closer to 0? Which one's the lower number? That covers everything. Lower number happens faster. That's lower than this, it happens faster. Negative 289 is lower than negative 284. 365 is lower than 368. It will happen faster. Whether we're talking about breaking or making, the lower happens faster. I think that was helpful. So your majors and your minors, major, minor, they both have benzene with a propyl group, para. Yes, I said para to a methyl. What's para mean again? Oh, as far apart from each other on benzene as possible. Major will be this one here with the BR here, and minor, the BR here. It happens slower. Oops, got to point that from the word minor. And there's a little note down here. Don't want to try to sneak that by ya. Once again, 368 was for this bond here. And 365 was for this bond here. NBS showed up at the bottom of this page. And what do we got going on with NBS? Nothing on the next page. Skipped it. How about the next page? I don't think it's there either. No. Was this an accident? Maybe. What am I going to say about NBS? What you need to know about NBS right here. Copy it. What you need to know about NBS. What do you need to know about NBS? I'm not even going to give you what it stands for because you don't need to know that. You want to read about it? There's a whole section in the book about it. One, it accomplishes the same result as Br2 and heat. All right, so you're going to get a radical halogenation reaction going because that's what happens with Br2 and heat with better results, as in higher percent yield and less side reactions. You want to read about those things? They're in the book, but you're not responsible for them. 2, the mechanism will be a bonus mechanism. It's kind of an advanced mechanism on the next test. And I will not be going over it. Don't panic. If you like bonuses, and I know there's a couple of you that do, it's in the textbook, the NBS mechanism. Answer keys for old exams have the mechanism on them. So feel free to look at all the old exams and see what kind of questions get asked with NBS in them, and they'll always have bonus written with them. Okay? So yeah, we're trying to stick with the basics this semester. Trying. And we got a new one here mixed with an old one. So a little story behind this. We learned we could put a bromine on the more substituted position. And the reason had everything to do with the mechanism. Reasonings have to do with mechanisms, not just using words and Russian guys' names. You know, that's not going to cut it. We got 2 carbocations. We have a major carbocation. We have a minor carbocation. This one has a major because it has more hyperconjugation. I need to see those magic words in your discussions of why you pick major products. And you got to talk to me about the rate determining step, which is forming the cation. Nothing about the products. And that would give the major result, which we saw here. What's going on here? Oh, that's a different reaction. We haven't got there yet. Here, the major is this result, which comes from the cation that has more hyperconjugation. That's all we need to do for that mechanism. And down here, some person tried to do that reaction at one time in history, probably close to 100 years now, maybe a little longer, but they got a different result. They didn't know they had something like this in here, this peroxide. It ended up being that there was a peroxide in there, and it changed the result. What normally would give the minor product, it was the major product. And later they learned that it wasn't even a carbocation mechanism. It changes when we have a peroxide and heat. So this mechanism, not as important as the Prop 1, Prop 2 mechanism we had a whole page on the exam. This mechanism is going to be like 6 points, not 26. And it's got a very different look to it. So the stuff he was cleaning with was the peroxide. And it does what's called Prop 1. You take your peroxide. And he was probably using hydrogen peroxide. It's a very common cleaning agent in organic chemistry and medicine. And what happens to peroxides if there's light or heat? They break down. It's homolysis, isn't it? And if you're keeping score, you get 2 of these. Oxygen radical, we haven't seen those. It's the only time we're going to use oxygen radicals. And there was a second propagation step too. This was found out decades after the accidental reaction was discovered. They figured out why he got the opposite result as before. And that reacts in a radical sense with HBr. We have not seen that before. The electronegative O is more interested in the more positive atoms, so they hook up. And this generates a different kind of bromine radical. We got a comment on this bromine radical here. This Br dot is different than Br dot generated this way. So we generated Br dot before. We had a carbon, like bromine attached to bromine, plus a carbon radical, good generic carbon radical here. And they hooked up. This was P2 from before, previous P2. And you also generate bromine radical. This bromine radical is a higher energy. Yeah, some molecules, they have the same makeup, but sometimes they're at higher energy or an excited state. And this one is a lower energy. This one. So that's how it's different than the other Br dot. So I call those prop 1 and prop 2. That's crazy. These are the ones that got the reaction started. Help me out, people. That's a rhetorical help me out. Don't say anything. What do you call the step or steps, in this case, steps that get the reaction started? We don't call them propagation. Propagation means keep the reaction going. This is initiation 1. And just for space, I'm going to call this init 2. So remember, before we had 1 initiation step, and that was our big mechanism. It takes a long time to get back in this program. Yep, there's our initiation here, and there was only 1 of them, so we just called it an init initiation. And now, I don't even know where I am. Page 4, I guess. My goodness. Okay, that's a preview. Here we are. Now it's time for prop 1 and prop 2. This bromine radical you just made doesn't like breaking sigma bonds. It doesn't have enough energy, but it can pop open a pi bond. Pi's are weaker, right? It'll pop it in half like this. Half of it goes towards making a bond. The other half goes to the other carbon, making a stable radical. P1 looks like this, and it generates the product that's indicated at the top of the screen. Or just above this, that's this thing right here. And it generates nothing else. So that's not like our other propagation steps. Now, why not Ooh. I'm having trouble separating things. It's because I'm using the wrong color, of course. Keep these away from each other. And the question is, why not this bromine radical plus the same pi, and we'll just go, the arrows will even look the same to start with. Half of it goes towards the bromine, and the other half goes over to this carbon. Okay, so that would give us another radical. Oh, wait a minute. I didn't finish with my first one, did I? You guys were nice and polite and didn't say, your hooks say there's going to be a radical on that carbon. There, now I finished it. And I realized that mistake when I did this. Oh, there's nothing there. Stop. I put the BR here this time. And the radical over there. Why not? Why is that bad? To make the radical there versus here. The answer is simple. Secondary, less hyperconjugation than tertiary, which has more hyperconj. That answers the question. Which radical are you going to generate faster? More stable tertiary. And then P2, that thing needs to get a hydrogen, so it's the major product. Where's it going to get a hydrogen from? Please don't forget that initiation steps, you only use like 1 out of a mole of this and 1 out of a mole of this. 1 out of a mole is 0. You have a whole bunch of HBr that you haven't reacted. And you want propagation steps to keep each other going. So, hey, you needed this bromine radical here. Where did you get the first one from? Well, this is initiation 2. But after you've used initiation 2's bromine radical, there's no more of that radical. But after you react this thing with HBr, there'll be more bromine radical. And very bold on that. You're picking up an H, and you're generating bromine radical that has the right energy, and you're generating your, what else? Your organic molecule that you desire. There's an H here. We don't have to draw it, but there it is. And in the end, when you analyze where the group went, it's an anti-Markovnikov result. Markovnikov. Oh, it's a dude. He's going to capitalize his name. Result. So we have a way of making anti-Markovnikov alkyl bromides. If you think this works with HCl, then you'd be mistaken. It's very limited to HBr, and you need a peroxide, and you need heat, and you get a reversal of Regio selectivity. Regio. Here's the Markovnikov. That's easy. Just treat it with HBr, no light, no peroxides. If you want the anti-Markovnikov, use HBr again, but have a peroxide present and heat, and you'll get the other product as major. Okay, and there's a little story there. And if you want to read the story, straight from the textbook right there. Talks about the accidental discovery of this reaction. And I think we're going to leave off there. Unless there's something down here. No. We'll be picking up with that physical properties of haloalkenes when we come back. And we'll see you then.